Hi, everyone. I know I sent out an email last night that said, have fun, you're on your own, but I woke up this morning and realized I can't do that. So here is a little video demonstrating to you exactly how to walk through the back page, the second page of the in-class assignment. Now, I'm not working the actual problem that I gave you, but I'm working an almost exactly the same problem, just with different numbers. You will have to do this with the numbers that are on your assignment in order to get different numbers for the results, but everything here is going to be the same. Start with the setup. Do corner lots get more complaints per year from the homeowners association than other homes? If they do, that's one thing. If they don't, then population one and the mu of population one, which is corner lots, will be less than or equal to population two, which is everybody else. Now, there were slightly different versions of this on the 9:30 and 11 o'clock assignments, but here's the thing. The prediction is in one direction. The predicted effect is that corner lots, population one, are going to get more complaints per year. That was supposed to be my tip off, that what you were dealing with was a one-tailed test. I didn't say, do corner lots get a different number of complaints? My prediction is that they get more complaints. So right up here, I've changed that or left it as a less than or equal to. Okay, on some versions it was equal to, and some versions it was less than or equal to. But let's just clean it up for clarity's sake and say what we're looking at is less than or equal to. So this is a one-tailed test. Okay. The prediction is that there is a difference of 7 complaints between population 1 and population 2. I've also given you the standard error for this design, S sub x bar sub 1 minus x bar sub 2. And in this example, it's going to be equal to 1.75. It's not that on your in-class assignments, but I'm making this new one up. Normal distributions for the sampling distributions, and alpha equals 0.05. So what is it that you do? I'm looking at the end of the game for 1 minus beta, that is to say, power. So if you want to take a look at the little graph, the little chart here that I have for you, tracing out this area here is where power is going to be. That is, if you're picking from the results you get if the alternative hypothesis was true, what proportion of them would cause you to reject the null hypothesis by being on this side of the critical value? So I'm looking for this area right here. Now, how do I get there? Well, that's why I had the steps below. So the difference of a certain size, that treatment effect is 7 complaints. But we can't really work in the units of complaints, which is why I asked you to translate everything into units of standard errors. So the first question I have here is how many standard errors separate the mu of the null distribution from the mu you'd get if the research hypothesis was true? Now, why is this 7 right here? Well, that's because if the null hypothesis is true, then taking the number of complaints from everyday houses and the number of complaints from corner houses will give you 0, because whatever they are, they're the same. So the null hypothesis is going to center around a difference of 0. But if the alternative hypothesis is true, then the typical result you'd get would be 7 more complaints for corner houses, which would make this distribution center around 7. This is a little bit different from the video that I put the night up, where I said like Verizon and AT&T. Verizon, they both have 5, or one of them has 8 for a difference of 3. I'm only giving you the difference right now because that's all that actually matters. So we could say that this distribution centers around 0. This distribution centers around a difference of 7. And so that effect there is 7. Now, how many standard errors is that? Well, every standard error is 1.75. So what we need to do is take 7 complaints, divide it by 1.75, and get the number of standard errors that separate this bar here, this line here, this mu here, from this mu here. Let's do that. 7 divided by 1.75 equals, okay, so there are, in this case now, 4 standard errors that separate the middle of those two distributions. Now what we're after is this: how many standard errors away from mu sub null is the critical value? So we're looking for this line right here as opposed to this line right here, and trying to figure out this section right here. How many standard errors is this section? Well, we can do that without any alternative hypothesis information at all. This is just figuring out where the critical value is, and the critical value is always based on knowing the null assumptions, nothing about the alternative. So what I would have to do is go over here to the Z table and figure out, if I have a one-tailed 5% in this green area here, how many standard errors would I have to go to reach that point? Well, Z tables don't deal with area beyond a point, they deal with area between a point and the middle. So if this area beyond the point is 0.05, then this area between the middle and that point will be 0.45, the rest of that half of the curve. So if the area, like right here, this area right here on the Z table is the equivalent of this area that we're looking for. So this area is 0.45. Let's take a look and see if we can find a 0.45 anywhere on this table. Oh, there's one. Between 0.4495 and 0.4505, there's a value. So somewhere between 1.64 and 1.65 is what we're working with. Let's go with 1.65. So the number of standard errors that critical value is away from mu is, from the Z table, 1.65 standard errors. All right. Now, you might not know why the heck we're doing all that, but really we're getting somewhere. If we know that this whole distance here is 4, and we know that this distance is 1.65, then clearly this is not going to be to scale, but all the concepts still work. Then we know that the distance from the critical value to the middle of the other distribution is the difference between the whole thing, 4, and the 1.65 that's covered by this distance. So in this case, it is 4 minus 1.65, which is going to be equal to 2.35. See how that works? So 4 standard errors in between these two peaks. 1.65 standard errors covers this segment, and 2.35 the rest of the way covers this segment. So now we know that all the points on the appropriate side of the critical value under the alternative hypothesis curve covers an area designated by 2.35 standard errors away from the mean, plus the entirety of the area of the other side of the curve. All right. Well, then the only thing we need to do is to figure out how much area right here there is. We know that that area starts in the middle and ends at 2.35 standard errors away. So let's take a look. I have to go to the second page of the Z table here. Okay, so 2.35. All right, that is 0.4906. So give myself some extra room here. From the Z table, 0.4906 area plus 0.5 for the other half here will give us this entire area that is to the right of the critical value and still under the alternative hypothesis curve. So that is, of course, 0.9906. That, ladies and gentlemen, is power for this particular setup. That is a nice, big, beefy power value. If this effect is real, if there are in fact 7 complaints on average worth difference between corner lots and the rest of the neighborhood, with a standard error of only 1.75, if we ran a hypothesis test, there's a 99.06% chance that we will reject the null hypothesis and say, yes, corner lots are getting more complaints. Okay, that's what power is. So walk that stuff through with your in-class assignment. If you're using a two-tailed test and you come up with 1.96 instead of 1.65, I'm not going to mark it off. I will roll with that and allow for two different correct answers based on two different reasonable assumptions. But that walkthrough really ought to be able to give everyone the tools to make it through this in class. I will also extend the due date to Saturday night instead of tonight to give yourself a little bit of extra time to view and absorb what I've got here. But best of luck to you all. I really know that you can do this. Take it easy, think it through, and I'll talk to you again on Monday night.